Hello again. So we suggested in our last video, or not so much suggested as told you outright, that the differential calculus is the study of how functions change. It's the study of rates of change. And we introduced this idea in the context of linear functions, which have constant rates of change. And I gave the slope formula, but I kind of wrong thing. Give me a second. I kind of uh went through it very quickly. So if we have a linear function, just envision this as a straight line. It's given by this equation, y equals mx plus b, and this m is the rate of change, but we've also mentioned that it's sometimes called the slope. And the slope gets described as the rise over the run. And you can take any 2 points on this line, and you can look at the vertical and the horizontal change. And the slope will be the rise over the run. And this ratio is constant. You might think, well, hold on, the rise and the run change, right? What if instead of using these 2 points, I used this point and this point? And now I have a new rise and a new run, but the ratio is constant. The ratio is always the slope. What's the rise and the run if we write them in function notation? You see, we're using function notation here, but not here. Well, in function notation, the points we select, the x-coordinate is A, the y-coordinate is f of A of this first point, and then here I'll call the x-coordinate B. The y-coordinate will be f of B, and the slope is f of B minus f of A over B minus A. And you don't know this yet, but this unassuming looking formula from high school algebra is one of the most important formulas in all of mathematics. All of differential calculus is based on this unassuming little formula. But how can that be when this formula only works for linear functions and the vast majority of real world functions aren't linear? Well, even if we don't have a linear function, even if our function is non-linear, this little equation still means something. We stop calling it the slope. If f of x is any function defined on an interval from a to b, the average rate of change of this function f of x on the interval from a to b is, well, we can probably guess how I'm going to finish this sentence. It's f of b minus f of a divided by b minus a. So if instead of talking about slopes, we talk about average rates of change, this quotient can be defined for any real world day-to-day function. There are a few restrictions, but we don't have the tools in our toolbox to talk about the restrictions yet. So, I mean, say we have a height function. We're going to toss an object up, and it's going to fall back down. And the input will be the time in seconds since the throw, and the output will be the height in meters, is what I'm most used to. Then this formula, this function, we'll actually see where this comes from before the end of this class, but a realistic function might look like this. F of t is negative 4.9 t squared plus 7t plus 1. And of course, this function isn't linear. This function isn't quadratic. So we can't talk about its rate of change the way we would talk about the rate of change of a linear function. But we could talk about the average rate of change. On the interval from let's say from 0 to 1. It's f of 1 minus f of 0 divided by 1 minus 0. So f of 1 is, let's see if I can do this in my head. We let t be 1. So 7 plus 1 is 8, minus 4 is 4, minus 0.9 3.1 f of 0. 0 plus 0 plus 1. This ends up being 2.1. And this 3.1 is a height, and this 1 is a height. It's measured in meters. Oops. And this 1 is a time, 1 second. And this 0 is a time, 0 seconds. It's measured in seconds. So this 2.1 has a unit, meters per second. You see the average rate of change of this height function is a velocity function.